going to continue with chapter 10. So last time we finished chapter 9 and we started chapter 10, and we started talking about probability, the mathematics of gamblers, right? So we talked about how probability was basically a number that described the chances of something happening. Right? So there's some event or an outcome and you want to figure out what are the chances of this event or an outcome. We can express this using a percentage, right? So we could say something like, there's a 70% chance that if you smoke, you'll get lung cancer, or something like that, right? Or we can express it as just a decimal number between 0 and 1. Again, I will take this opportunity to say, if you ever give me a probability outside of this range, there is no forgiveness, right? You get 0, okay? So there's, you weren't here for that, so I'm gonna make the threat to you in particular. Do not give me a probability outside 0 and 1, okay? So there's a number between 0 and 1 inclusive that describes the chances of something happening, right? 0, probability of 0 means the event is impossible, can't happen, right? Probability of 1 means the event is certain, right? There's a 100% chance, right? And any other situation falls somewhere in between this, right? So we talked about sort of where this math came from. It really came from gambling, right? People wanted to find out, the chances of, if they play this game, what are the chances that they'll win, right? And they enlisted the help of mathematicians to help them figure it out. But it grew into a lot more than that since then, and the applications of probability and statistics are far-reaching, right? It's not just something mathematicians and engineers care about. Like, a lot of people in all walks of life will care about probability and statistics. So the next thing we talked about is how this can sort of be counterintuitive, right? So sometimes it seems obvious that oh yeah, the chance of that is this, right? Sometimes it's not obvious at all. We're going to be dealing with those situations. And there's sometimes where it seems obvious, where it's not really. So we talked about the Monty Hall problem, right? Where I was like, oh yeah, would you switch? Do your chances increase if you switch? Everyone was like, no. Like most of you are like, no. Turns out, yes, right? You're 2/3 more likely to win the car if you actually switch your door, right? And we talked about the 3 prisoner problem, and that was counterintuitive as well. And we sort of left things off at another problem that is also going to be probably counterintuitive. So let's just pick up with that. All right, so we suppose a couple has 2 children. Right? And of course, we're assuming that the probability of having a boy is a half, probability of having a girl is a half. Right. So A, I want to know what are the chances that they are both girls? So that seems like, okay, yeah, we can sort of figure that out, okay, but then I ask, what's the probability that if we know one is a girl, what's the chances this other child is a girl? Right? And you might think, well, that shouldn't really be any different. We still have 2 girls. It turns out it's very different, and you'll see how. C, we wanted to figure out, what if we know the older child is a girl named Freuda? Right? What are the chances she gets bullied in school? No. What's the chance the other child is a girl? Now, intuitively, these don't really seem like different situations because we have 2 girls in all cases. Turns out they're actually very different. Right? So this is one of the reasons why these rules that I'm going to be telling you probably are very important, because a lot of times your intuition can sort of lead you astray. You have to be very logical and delineated in how you do things, and the rules will help us get to that. So, did anyone actually try this? Try to figure it out? No, you guys totally. Okay, let's try to figure it out now. A. Okay, so we know a couple has 2 children. They're both girls. What's the chances that? What are the chances that they're both girls? How do you think we'd go about this? Give me some sort of, yeah?
Well, for the first one, it'd be half and half, right? So it would be 1/2 plus something else to start out with, right? Yeah.
Sorry, how would you express that? How would you write that down? And why do you think it would be a half plus something else? Why do you think plus is?
Or would it be times? It would be times because it's both instead of like one child, right?
Mutually, so yeah, we're going to talk about that later as well. When do you know you use times and when do you use add? But try to think more elementary here. Try to think of the cases. Like, how would you express what's going on? How about we try to say, write out the different scenarios. So what are the different scenarios, right? Let's say we have the first child and the second child, right? What are the possible scenarios? The first child could be a boy and the second child could be a boy. That's one scenario. Or we could have a boy and a girl. Or we can have a girl and a boy. Or we can have a girl and a girl, right? So these are sort of the situations. Now let's look at what are the chances of the situations. Now remember what we said about probabilities last time. Probability of something happening is, we could think of it as the number of ways something is possible to occur out of the total number of possibilities. So what are the total number of possible ways you can have 2 children? There are 4 possible ways, right? How many ways can you have 2 girls? There's only 1 possible way. So in part A, the probability of 2 girls is simply 1 out of 4,
So
right?
it's half times half.
So it's half times half. We haven't covered that concept yet, but we're going to get to it. It would be a multiplication, half times half. Now what's B? Same answer, right? It's not going to be the same answer. Why? What makes B different?
Because there's only 2 possible scenarios there. Because you already know one of them is a girl, so it's not 4 possibilities, there's only 2 possibilities. And the second child could either be a boy or a girl.
It's 3 possibilities,
We don't know
right?
if it's the
Oh,
first.
because
Remember, we don't know that the other one is not a girl. We just know that there's at least 1 girl in this pair, right? Which means in part B, we really have these possibilities. It's either a boy and a girl, or a girl and a boy, or a girl and a girl, right? This situation is no longer a possible situation for us, right? Because we know that 1 has to be a girl. So obviously having 2 boys is not on the table anymore. So now, try that if one is a girl, the other is also, is actually what?
Oh, it's also. Sorry, no, that was in my head.
That was in your head? You
I
said that
something
out loud.
yeah.
Yeah. This one is actually 1 out of 3. So you can see here, it's actually a completely different answer from the first one. Right? In both cases, we had 2 girls, but our situation actually changed. The chances of something happening actually changed because we were given information that cut down on the number of total possibilities we had. Right? What about the third case? So we know the older child is a girl named Freuda. Right? What's probably that the second one is a girl? So now what are the total possibilities? Now there are only 2 possibilities because we know that the first child has to be a girl. So we can only have G's here. Right? Which means you can either have a boy or a girl on the second one. This means probably that the second is a girl given first is a girl, is now 1 out of 2. So this is the reason why. And underlying all of these, there are rules of probability that we're using, right? Like someone said, you know, there are times when you multiply, when you add. We're going to actually uncover all that. But a lot of times just having a diagram help you reason through all the situations is a great help. And you can actually get to an answer a lot of times without really knowing a lot of probability theory. But I am going to show you the theory for all this. But I just want to emphasize that you can't always count on your intuition. There can be situations that seem similar, seem obvious, but they're not. There are a bunch of ways that you can have 2 girls if you have 2 children. And the chances for all these are different. Okay? So that sort of emphasized the need for all these rules that we're going to be talking about. How a situation can really change the chances of something happening, just depending on the information that you have. By the way, something else we'll get to later on, these last 2 here, the idea that you can have the chances of something happening given that you know something else happened before, it's called a conditional probability. We'll get to that later. It's just sort of a preview of where we're going. There's a lot of things happening in the background here that we're going to be getting to. So we already talked about how we define a probability. And the second one, now we're going to talk about counting. Counting in probability is actually very important, right? You've seen, essentially what we've been doing is we've been counting and taking a ratio, right? Count the number of total possibilities, count the number of ways what you want can happen, and then you divide the 2, right? Obviously counting is very important. It turns out that sometimes counting can get very difficult, right? You can have situations that branch off into other situations, and figuring out how to count things then becomes an issue. So we have to talk about actually counting. It might seem easy, but again, that's your intuition leading you astray. Counting is not always easy. Let's actually talk about counting. Right? In future chapters, we're going to talk about combinations and permutations and more efficient ways to count, but now let's keep it simple. The first way we're going to look at is called the multiplication rule. Okay. So let's say we have a multi-stage experiment. And in the first stage, there are m possibilities. M1 possibilities, M2 possibilities in the second, M3 possibilities in the third, etc. Then total number of possibilities is, what do you think it is? Right, multiply them. M1 times M2. Multiply as many as you need to. So this is a way to count the total number of things. If you know that something happens in stages, and you know the total ways that something can happen at each stage, then the total number of possibilities is just a multiplication of all these numbers. So let's look at an example. Different color shirts. Different color pants. Of course, you're ignoring fashion. No, this color doesn't match that. Ignore that, right? If you have 3 different color shirts, 2 different color pants, how many different outfits can you make? 6. Right? So in this case, you can sort of think of stage 1 as the shirt stage. You have to pick a shirt. Stage 2 is the pants stage. You have to pick a pants. This signifies total number of outfits. Is just 3 times 2. You make 6 total number. 6 total outfits. Okay, let's look at something else. What if you toss a coin 3 times? How many outcomes are possible? B. Follow-up question, what is the probability of getting 3 heads? Okay, so someone says, you know, toss this coin 3 times, you get 3 heads in a row, I'll pay you $100. It's just a $50 buy-in. $50 buy-in, you toss 3 heads, $100. I just, no question asked. Do you take the bait? So first we have to figure out how to count these. What are the total number of possibilities and how many ways can I get 3 heads so I can figure out what my chances are of winning at this game. What do you think is the answer to it?
6. 6.
Why 6?
Oh, never mind.
No,
Oh,
because
never
there's
mind, yeah.
2 different ways it can be, and then 3 times. Oh wait, that's 6.
Don't forget the multiplication rule. What should you be multiplying? You should be multiplying the number of possibilities together at each stage, right?
Yeah.
So in this case, the stage is the tosses, right? So one stage is the first toss. The next stage is the
So it's
second
2
toss.
times 2 times 2.
The next stage is the third toss. Right? Now here, there are 2 possibilities. And for this one, there are also 2. For this, there are also 2. At any given stage, you can only get a head or a tail. So you have 3 stages, because you're making the toss 3 times, but there are 2 possibilities for each stage. This means 2 cubed equals 8, the total number of possibilities. There are 8 possibilities for how this thing can turn out. B, what are the chances of getting 3 heads? There's only one way to get 3 heads. You have to literally just toss 3 heads, right? That's the only way to get it, right? There are actually several ways to get 2 heads, but there's only one way to get 3. You'd have to get 3 heads all in a row. It has to be head, then a head, then a head. And so there's only one way. This means the probability of 3 heads is just 1 out of 8. There's another way I want to illustrate this that your book talks about. It's called a tree diagram. It's a nice diagram to have when you're doing a multi-stage experiment, provided that the total number of possibilities doesn't get very huge. So-called tree diagram. So basically it starts at a point and it branches off based on the options that you have. So on the first stage, there's the first toss. Right, when you're at that level, that stage, right, there are only 2 possibilities. You can either get a head or you can get a tail. Right? And then in this situation, again, there are 2 possibilities. Right? So on the second toss, you can either get a head or a tail. And then again, this stage breaks down into 2 possibilities. For the third toss, you can either get a head or a tail. The same thing can happen here. You can get a head or a tail. Same thing will happen here. Right? We're just trying to diagram all 3 possibilities in this tree-looking diagram. Now if you can draw this diagram, the last step actually tells you the number of total possibilities, right? 8 options on the last step. This means 8 total possibilities. So this is sort of drawing a tree diagram. We could have done this situation with having the 2 girls problem, right? We could have, oh, it can be a boy or a girl, and then you split up to boy and girl and boy and girl. You realize you only have 2 stages in that experiment, and so you'd have 4 possible options for the general case, and you can actually break these down later on. Right? So now, if you have this diagram, how would you actually get to a probability? The number of arms. Give you what you want. So let's say we can answer question B again, but using the diagram as a guide. We want to get 3 heads. So now we're pretty much going to count how many arms will give us 3 heads. You start at the top and you just run along an arm. To get 3 heads, you need the first one to be a head, the second one to be a head, and the third one to be a head, right? You see this arm here has 3 heads. Is there any other arm that has 3 heads? No, if you run along here, you'll only have 2 heads. Here you only have 1 head. Here you only have 2. If you run along here, you only have 1. Here you only have 1. Here you have none. Right? There's only 1 arm that gives you what you want. There's only 1 arm that has 3 heads on it. Right? So there are 8 total possibilities because there are 8 things on the last stage. And there's only 1 arm that gives you what you want. Let's do another follow-up question. What's the probability of getting 2 tails?
Only 2 tails or?
Exactly
more
2 tails. Exactly 2 tails.
So 3.
Yeah. So which arm gives you 2 tails? Well, not this one. Going here, here, here will give you 2 tails.
To the right.
Going here, here, here gives you exactly 2 tails.
And then right, left, right.
Going here, here, here gives you 2 tails. Is there any other arm that will give you 2 tails? So 3 arms have exactly 2 tails. This means probability of 2 tails is equal to 3 out of 8. By the way, what's 1 out of 8, by the way, just as a decimal? 0.16.
1, 2.
0.125, which is pretty much 12.5%. Right, so by the way, if you took the bait here, you only have like a 12.5% chance of winning that $100. Is that something you put up $50 for, the chance? 12%?
Still a greater chance than winning the lottery. And by
A far
percentage.
greater chance than winning the lottery.
By such
But
percent.
the thing about the lottery, the incentive is like, it's only a small buy-in. But of course, enough people buy into it.
So it's like a lot, yeah.
At least in the short run, you know, you have some people buy the lottery like every day. But yeah, the chance of winning a lottery, way small, way small. Right? So this is sort of the idea. You know, you can use diagrams, you can use tables, you can just break things down by cases. But the idea is never go into this thing thinking by your intuition. No, oh yeah, it seems possible, it seems likely. No, you have to break things down because it can get very counterintuitive. And these are just some of the ways. Knowing a multi-stage experiment, once you can read a probability problem and realize, oh, this is a multi-stage experiment. There's just something happening at each stage. These are the total number of possibilities at each stage. You can figure out probabilities just by recognizing that. Right? And a lot of times you can draw diagrams to help you, like a tree diagram is pretty popular. The problem is they can get cumbersome pretty quick. Like if I did 4 coin tosses, I'd already have like 16 possibilities down here. Right? 5, I'd have 32 possibilities, right? It can get huge and cumbersome, but for small enough things, it's a nice diagram to use to your advantage. Let's see, do I have another example? More examples. In probabilities, there are tons of variations. We did a similar problem to this last time. Do that question, or to put a wager on it. For example, sort of subjective. Any questions so far, by the way? Are we getting this? The important thing is getting the rules and techniques down. Once you start trying to wing it, that's when you get in trouble. That's when students start to mess up with probability. Winging it is dangerous. These are all examples of multi-stage experiments. It might not be phrased in that way, but you should be able to recognize when one is staring in the face. These are all multi-stage experiments. Okay. So this one we should know how to approach because I actually jumped the gun and gave you an example of it last time with the sum being 7. So how many possibilities are there?
36.
There were 36, right? In this case, again, we used the diagram to help us figure it out. Right, we're distinguishing between the dice, so the numbers on each die we are thinking of as different. So this is 1, 2, 3, 4, 5, 6. All right, so you can get a 1 and a 1. 1, 2, and 3, 1, 4, 5, 1, 6. 2 and a 1, 2 and a 2, 2 and a 3, 2 and a 4, 2 and a 5, 2 and a 6. Not writing these as a sum in general. Five and 1, 5 and 2, 5 and 3, 5 and 4, 5 and 5, 5 and 6. 36 total possibilities. For B, what's the probability of getting the sum to be a 5? Well, we'd have to figure out in which stages do we actually get a sum of 5. Well, 4 and 1 we'd get it, 2 and 3 we'd get it, 3 and 2 we'd get it, 4 and 1 we'd get it. And that's it. There were 1, 2, 3, 4 ways. Four out of 36, which is 1 out of 8. So there's a 12.5% chance that the sum is 5. Now, again, you have to really be careful how you're reading these problems because sometimes, yes, 1 out of 9, yes. So another thing you have to be aware of is you have to really be careful on how you're reading things. Like, for example, this sentence here is actually pretty important, right? Because that's basically saying we think of getting a 2 and a 3 and a 3 and a 2 as different outcomes, right? So we're actually distinguishing the situation where the first die gives a 2 and the second gives a 3. We think of it as different from the first one giving a 3 and the second giving a 2. If you said that we're not distinguishing between the dice, then half of this table would be gone, right? Because every time you switch the two numbers, we're recognizing that as the same thing. So things like that you also need to be aware of, right? Be very pedantic on how you're reading the questions. Right? There are going to be times where we're talking about, we're picking things and we might replace them or we might not replace them, and that will change the entire answer, right? So be careful how you read. Figure out an efficient way to write down the information that you're given and an efficient way to count the information that you're given, and that's sort of how you want to approach this. Any ideas on how to do this one?
10 to the 9th.
All right, so again, this is a multi-staged experiment. What are the stages?
Each number
The
has
digit
10
places,
possibilities.
right? So in part A, we have 9 digits. 1, 2, 3, 4, 5, 6, 7, 8, 9. You can think of each of these as a stage, right? And now you have to figure out how many options do we have for each stage. So how would we figure this out? So we're told the first digit must be a 1, which means there's only one option for this. It has to be a 1. Right?
You go on the line then. It's 10 digit.
No, it's a 10-digit phone number where the first digit must be a 1. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So now the first digit has to be a 1. So I have only one option there. I have to put a 1. How many options do I have for the second stage? There are 9 digits. There are 10 digits. Because we said there are no restriction otherwise here. And what for this one? Well, 10 digits, right? We'll have 10 digits because there's no other restriction on the numbers we can pick. So this means the total number of phone numbers is 10 to the 9. Billion different possibilities for phone numbers here. B, we add a restriction. What if the second number, the second digit is what I should say here, just to emphasize. What if the second digit cannot be a 0? How does that change things? Right, so it means the first thing has to be a 1. The second thing, you also have one option, right? So this must be 1. The second digit, you have 9 possibilities. 9 possibilities. Since you can't choose 0. So you only have 9 other digits to choose from. And then everything else remains the same. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And no restriction otherwise. So this means there are 9 times 10 to the 8. 1, 2, 3, 4, 5, 6, 8. Possible numbers. 900 million ways you can get a phone number with those restrictions. Now, if you have such a phone number, like this one in B, and you have a stalker who's trying to guess your phone number, what are the chances he gets it right on the first try?
1 out of 9 out of 10 to the 8.
900 million.
Right, he'd have to guess your one correct phone number out of all the possibilities. As a decimal, that's like 0.00003. There are a lot of zeros there. Yes?
So for that question, you would assume that the stalker knew the conditions? That like the first one had to be a 1?
Yeah, I mean, in general, the phone formats are something that's publicly known, right? You'd know that, well, you know.
Right.
So like, if you knew, well, I mean, if you knew a phone format, you would probably know your area code. So if you like doing that.
Yes, but I'm just saying in this situation, it's worse than that. In D, he knows 7 digits of your phone number,
It just needs to be in the right area.
right? So
Hopefully you're
I'm saying a blind guess. All he knows is that the first digit is a 1 and the second one cannot be 0. If he were to guess your phone number, those are the chances of him getting it right. So, you know, it'll take forever for him to guess your phone number. You're probably safe. He'd need more information, which Depends on how much he wants to contact you. Okay. All right, so D, what if he knows the last 7 digits?
And first.
Wait, the last 7?
Yes.
And
And the first two.
The first 2 are obviously also have that situation, right? So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So he knows there's 1 option here. There are 9 options here. And 1, 2, 3, 4, 5, 6, 7. So these are all known. So he knows those. He doesn't even have to guess. He actually knows the last 7 digits. So how many guesses would he have to take here?
10.
10. Which means there are only 90 total possibilities now. So if he dials a number a minute, he'll figure out your number in like an hour and a half. Yeah. So probability of guessing correctly is now 1 out of 90. So really, behind all these problems is the fact that you can sort of think of them as multi-stage experiment, where you can somehow think of something that's happening as a different stage from something else. And then if you know the total possibilities of each stage, you can figure out the total by just multiplying them. This is actually applying the multiplication rule. And it's just a very efficient way to count things. And so just imagine if your method of counting was actually writing down all the different phone numbers you can think of and then counting them. You'd have to guess 900 million of them. You'd never get done. But right, you know you can figure out that there are 900 million without actually counting to 900 million by using the multiplication rule. So it's a very efficient way to count when you know a situation is a multi-stage experiment. And we'll cover more efficient ways to count when we get to chapter 11, but for now that's one of the main rules, the main counting rules we'll have. There are other rules. I said this already, but it's worth repeating. There is 0-1 principle, it's called. That says a probability of we mentioned this last time, but it actually has a name. It's called the 0-1 principle. That means for an impossible event, the probability is 0. For a certain event, the probability is 1, and in all other cases it's going to be a number in between these. And there's another rule that we should know. The sum of all probabilities what must the sum of all probabilities be? 1. Right? There's a 100% chance that something will happen, even if we don't know exactly what. And so that's something else you have to look out for. So let's say you have a situation where there are only two possibilities, and you tell me, okay, so the probability of the first is, 0.9, and the probability of the second thing is 0.8. Then even though in each stage you got a number between 0 and 1, it's not really a cause for concern. The fact that you can sum up these possibilities and get something bigger than 1 is a concern. It means you made a mistake as well. Right? If you sum the probabilities of all situations, the answer must happen to sum to 1. And this leads us to another rule. It's called the rule of complements. It's actually a super useful rule. It's very useful because sometimes it's easier to figure out when something will not happen as opposed to when it will. And we're going to see a lot of examples where that's the case here. Right? So if A is some event, something I'm looking for to happen, a complement, which is A to the little c up top, is the notation. That's the event that A will not happen. Right? So if you're tossing a coin and you say A is the event that I get ahead, then a complement would be the event you don't get ahead. In other words, you get a tail. Right? It's just what you want does not happen. That event is called the complement event. And since for any event A, either it will occur or it won't, we have the probability of A plus the probability of A complement must be 1. Right? Either it will happen or it won't. Right? For any event, these are the only two cases. Either it's going to happen or it won't. Right? You toss a coin, you're either going to get ahead or you won't get ahead. There's no other possibility. Right? So the sum of the probability of something and its complement probability will always be 1. Always. Sometimes people prefer to memorize it in one of two ways. Probability of A is probably 1 minus probability of A complement, or probability of A complement is 1 minus the probability of A. So you can memorize it that way if you want. But the sum of all probabilities must be equal to 1, and for any given event, the probability of it happening or not is 1. Right? It's certain that it will or won't happen. So let's look at a situation where this can actually come in handy. Toss a fair coin. So the idea is, why would we care about this idea? It can help us solve problems a lot of times. We toss a fair coin 3 times. What's the probability of getting at least one? That's probably at this point I should introduce some language. In general, at least 1 just means greater than or equal to, right? So at least 1 means 1 or more. At least 2 means 2 or more. At least 3 means 3 or more, right? Another thing that you'll see often is at most. Well, that's less than or equal to, right? So this is 1 or less. And so just, it's very common language to see this, right? At least means that greater than or equal to. At most means less than or equal to. For future reference. Ideas on how to tackle this?
So you have 3 options, 1 head, or no, 4 options, 0, 1, 2, or 3 heads. So wouldn't we go for the complement where we look for 0 heads?
There's only one way of getting no heads.
Yeah.
Right.
1 out of that one way, which is 1 out of 8. 1 minus 1 out of 8.
Right. So here, again, we actually did the tree diagram for this earlier. Here we have 8 total possibilities. Now you can appreciate the fact, hopefully you appreciate the fact. Maybe I should draw it out so you can see what I'm talking about. And this will make you appreciate the fact that this is a 3 here, it lets you off easy. I could easily say 10, in which case you'd have 2 to the 10 possibilities. Drawing a tree is going to be impossible. You'd like freak out. And just because something has 2 options makes it even easier. Like in general, a question like this can get really hairy if you want to draw it out. And this is the guy that's going to save you. Because sometimes thinking of all the other situations is really hard. But thinking about the opposite of the situation is really easy. Right? So let's say we wanted to brute force this, right? We want to figure out, okay, how can I get 1 head or 2 heads or 3 heads, right? So then you have to think, well, I can get a head, a tail, and a tail, or I can get a head, a tail, and a head, or I can get a head, and a tail, or a head, and a head, and right, and you're going through the possibilities, and you're thinking, okay, that way I can get 1, this way I can get 2, right? And you're trying to count through all the possibilities, right? This situation is not that bad, but it could easily get a lot worse. And you thinking of all the ways to get this thing to work is going to be crazy, right? And this is a rather easy example. It's just an illustration. However, think of the opposite. How can you not get at least 1 head? There's only one way. You'd have to get all tails. That's the only way to not get at least 1 head, right? So, there are 7 ways to get at least 1 head, but these might be difficult to think of. So we think of the complement, which is what's going to happen here. So basically, I want the probability that the number of heads is greater than or equal to 1, right? Now this is just going to be the probability of 1 minus the probability that the number of heads, the opposite of being greater than or equal to 1 is being what? Less than 1. In other words, this is just 1 minus the probability that the number of heads is 0. But there's only one way for that to happen. There's only one way to get no heads. This means all tails. Well, since there are 8 possibilities, there's only one way to get all tails. It means the probability of getting at least one head is 3 out of 8. So sometimes counting the number of ways for what you want does not happen is actually easier than counting the ways for what you want to happen. And whenever that situation arises, you can use the rule of complements. You can think of the complement probability. Right? The probability of what you want is 1 minus the probability of what you don't want. That's probably a good way to think about it. I should write that down. Think about what you want, and think about everything else, and figure out which one is easier to count, right? If it's easier to count what you don't want, you use a complement, right? If it's easier to count what you do want, you just do it the direct way that we've been doing it before. In this case, and in many other cases, as we'll see, sometimes it's easier to count what you don't want. It's much easier to count the number of ways to not get any heads at all, as opposed to the number of ways to get 1, or 2, or 3, or 4. Right? So that's another rule that will help you. Any questions on this? Here's a situation I want you to think about and try to tell me next. It's actually easier. It's easier to tackle it using the rule of complement. Right? It's also another famous kind of problem. You have 10 people at a party, what's the chances of 2 of them having the same birthday, at least? Can you think about that and tell me next time? It's actually very counterintuitive. In fact, I forgot what the number is. I think it's like 25. But I think it's 25. Yeah, there's like the case where if there are 25 people at a party, the chances of 2 people having the same birthday is actually more than a half, right? Which means, relatively speaking, it would be strange if 2 people did not have the same birthday. Right? So in fact, in this class, there are 40 students. It will actually be strange for 2 people to not have the same birthday in this class. Right? It's actually more likely that 2 of you share a birthday than it is 2 of you won't. Right? Which
Same day, not necessarily the year, right?
Not necessarily the year, the same day. Right. It's actually more likely for that to happen. If I had a gun to my head and I had to bet money, I'd bet that 2 people here have the same birthday. Right? It might not always happen. I'm not saying it's certain. It's definitely, the probability is definitely not 1,
There's like
but there's actually a higher, what?
It's like 365 different days.
I know. Like I said, counterintuitive, don't trust your intuition, go by the rules, right? If you actually do this problem, work it out, you will realize, yeah. It's actually greater than a half if you have 25 people or more. The more people you have, the higher the chance. But yeah, it's actually more likely than not that 2 people in this class have the same birthday than not. I know it's crazy to think about, but it's true. It's more than half as likely. And again, to tweak this problem, it's not that hard. I could actually ask you, what is the probability that one of the people share your birthday? The answer is actually different when you think of it that way. Again, don't trust your intuition. Just thinking of 2 random people having the same birthday is different from picking a person and then saying someone else has the same birthday as that particular person. It's actually a completely different situation, different probability. So, but it's still pretty likely, actually. So if you're forced to bet money that 2 people have the same birthday, once the group is bigger than 25. I think 25 is the number, right? I guess I have to look that up. Maybe I'll give that a second question. What's the probability at least one of these people?
I do at the point.
At your birthday. If you're one of the 10. So suppose you're actually attending the party, you're one of the 10 people. What are the chances that someone else has your birthday in particular? They're actually not the same thing. Not the same number, not the same chance. It might be better to wager one versus the other. But again, they both get very likely once you pass 25 people. Another thing that should help you, which we actually touched on earlier, more general is actually probably the wrong word. More particular. So this is true for a multi-staged experiment. You can think. I want to emphasize this is not a general rule. There are situations where this does not work, but for a multi-stage experiment, it does work, right? And there's another situation where it does work, which is in independent events, the AND will work, and in mutually exclusive events, the OR will work. But the idea is you can think of AND as multiplied. And you can think of or as add. So if someone says, what is the probability of this and that happening? You think of multiplying the two probabilities. What's the probability of this or that happening? You'd add the two probabilities. And again, not in general, for a multi-stage experiment we know this is true. And there are a couple other cases where we know it's true that I'm going to define specifically later on. But don't think that this works in general. But if you know you're in a certain situation, this does work. And you can literally translate the word and to multiply and the word or to add. Yes, the dress code says you have to wear pants. I know, it's like, what's the word? Pants and a jacket. Or necktie. Or both. A jacket and a necktie. This is actually the last example of this section. In the beginning of the next section, we're going to get very particular with this situation. When exactly can you use and or as multiply and add? Right, but for now, let's actually work through this problem. Now, we did an example of this earlier where we said, you know, suppose he has 3 shirts and 2 pants, how many outfits can he make? And we saw, oh, that's like a multi-stage experiment. The first stage is choosing a shirt. The second stage is choosing a pants. In the same way, this is a multi-stage experiment, so this actually applies. So pretty much, you're going to read the question carefully, and you're going to figure out, oh, here they're using and, or. The language actually hints to you what you have to do, right? When you know it's a multi-stage experiment, or a mutually exclusive versus an independent event. We'll actually end with this example, so I'll give you guys some time to try to think about it, see if you can come up with something. By the way, something else to write down. So our third test is after we cover chapter 11. And if we get through that quickly, I can actually finish that in one class. Well, it depends on how many questions you ask on the homework. But at the latest, I expect to finish that next Wednesday, which means the third test would happen the following Wednesday. So tentatively, it's going to be April 29th. Test for what? Someone say something? Test for is the last day of class. Which I believe is the 15th. Is May 15th. If I'm not mistaken. I had the calendar here. Had the calendar in the syllabus. It's the week of the 15th, so it'll be the 13th, which is a Wednesday.
Then we have the final.
Yes, and then with the final, it's on the what? I also put that date on the syllabus, so the final would be the 21st. The 21st? Oh, we have a lot of time.
We don't have 20 minutes because it's finals week, so we don't have class.
Yeah, I lost some classes.
13.
Yeah, a week and 1 day later. It's the 21st?
Yeah.
That's like a Thursday.
Yeah.
Why would they put it on Thursday?
So we can conflict with our other
So it can
classes.
conflict with all your other schedules. All right, let's do this and get out of here. How do we do it?
So you, for all of them, so what you're gonna need is shirt, pants, and then you have from there 3 different scenarios. A scenario with the jacket, a scenario with the necktie, and a scenario with the jacket and the necktie.
Okay, so let's actually write down. So one of the ways to do this, especially if it sort of hints to you that and and or is in play, I'd actually write down the situations, rewrite it down concisely and clearly using and or to connect things, right? So what is the first situation that we want?
Shirt, pants,
He must have a shirt and
pants,
pants.
and
To
jacket,
wear pants, right?
and a jacket.
And a jacket, right? Or the second thing, the second kind of outfit he can make is shirt and pants and jacket and tie. Or he can have a shirt and pants and tie. Does that cover all the possible outfits?
Yeah.
You must have a shirt and a pants, so in all situations you must wear a shirt and pants, right? And he can wear a jacket, so that covers this situation. Or if he wants, he can wear a jacket and a tie, or only a tie, or only a tie, right? So this covers all the possible scenarios of the kinds of outfits you can make. You can make this kind of outfit, or that kind of outfit, or that kind of outfit. Notice that I rewrote it with and or, because I'm literally going to directly translate these guys into multiplication. So all the ands I'm going to translate to multiplication, and all the ors I'm going to translate into addition, right? So, number of possible outfits is, well, remember this is a multi-stage experiment. In the first stage I'm choosing a shirt, then a pants, then a jacket, right? So how many ways can I do that? Well, there are 3 ways to choose a shirt, times, because and. There are 4 ways to choose a pair of pants, and there are 2 ways to choose a jacket. Or, I put a plus. There are 3 ways to choose a shirt, 4 ways to choose a pair of pants, 2 ways to choose a jacket, and how many ways to choose a tie? How many ties? 4 ways to choose a tie. Or 3 ways to choose a pants, 4 ways to choose a shirt, and 4 ways to choose a tie. So now you, what is this?
168.
It's 168 total. So this is another counting technique, because sometimes, as you can see here, trying to count all the ways for something to happen, it's sort of difficult, but a lot of times the language helps you, knowing it's a multi-stage experiment helps you. There are all these techniques that we can use that makes our life easier. Once we know how to count well, we can know how to find probabilities well, right? So one situation is, in a multi-stage experiment, you can usually translate and or into multiplication and addition, respectively. And there are a couple other cases where this works, but this is not something that works in general. For example, if it's not a multi-stage experiment, don't assume you can do this, right? Or if it's not, next time we'll talk about other situations where you can do it. You can't do it in all situations, but in a multi-stage experiment, you can. At least does it. Yeah, well, yeah, he doesn't have to choose. Yeah, that's some freedom, yes, yeah. Okay. We'll stop there. We'll pick up next time with chapter 11.